Okay, we're going to talk about simple harmonic motion. We're going to try to talk about it without a lot of the jargon or the sinusoidal equations that go with it. Not because those things are bad, but just because it's a simpler place to start. Simple harmonic motion means a lot of different things. Let's take a look at some of the things it doesn't mean. Okay, it doesn't just mean back and forth motion. Just because something moves back and forth like a tennis ball against a wall doesn't mean that it's simple harmonic motion. But it could be something back and forth. All simple harmonic motion has something that moves back and forth, side to side, up and down, something like that. So that will be included. Doesn't mean it's periodic. Like I said, the example of tennis ball hitting back and forth on the wall, that is periodic. It's going to come back to your hand if you throw it the same way every time, the same time. But simple harmonic motion is periodic. The thing that makes it different is that it moves back in its periodic motion about an equilibrium point. There's going to be some point in the center that it wants to settle into if it can. If it was allowed to settle, move forever, or if it was allowed to, it would get back to that equilibrium point. That's where it would sit if you didn't move it away from it. And the restoring force is going to increase as you move further from equilibrium. Like the ball against the wall, it doesn't matter how far I am from equilibrium, right? I throw the ball, I have to push against it every time to get it to go against the wall. The ball pushes it back, comes back to my hand. That's not really, there's no equilibrium point in the middle. If I threw it far harder, it would just go further away. And the restoring force, the equilibrium point doesn't matter, doesn't affect the equilibrium point or the force. All that affects the force is my hand. Okay, you can see a good example of that is the spring there with the mass on it. As I move it further away from that resting point, it's going to want to get back to that resting point. So that spring is going to pull harder and harder the further I pull it to the right. The same is true by pushing it to the left. If I compress that spring, it's going to want to push back to the right and get it back to that equilibrium point. That's what makes simple harmonic motion. So based on that definition, how do you decide if something is simple harmonic motion? Let's look at a couple of examples and feel it out. First, we got a car moving in a circle. So it's just moving around in a circle, like on a track or something like that. Well, is it periodic? Well, if it moves around in a circle like at a constant speed, yeah, check mark. So far, it sounds like it could be simple harmonic motion. But is there an equilibrium point? Is there like some point that the car is going to settle to if the car is moved on its own? Nope, that's not simple harmonic motion. That does not work. Okay, okay, okay. Let's look at another example. The pendulum moves back and forth. So it's going to move from side to side, like a pendulum, like on a clock. Well, that one's periodic. Well, it's a pendulum, like it's used on a clock. That's going to work. How about an equilibrium point? Well, if the pendulum was just let to sit there, it would just sit in the middle. So it's always trying to get down to that middle, like where it can hang straight down. That's the equilibrium point. Now, restoring force. This is kind of tricky and slightly debatable. Okay, but it does have restoring force because gravity is always trying to pull it back down to that center, right? So that is, or has a restoring force. Okay, and so that one is simple harmonic motion. So that's how you can tell. Look at first periodic, has an equilibrium point, and if it has a restoring force. Now, how do you know a distance that you're given as an amplitude? Okay. It has to be from the center of motion, the equilibrium point, to the edge. That's the only way you get a real amplitude. Okay. You can see it in the picture. Okay. You can see that there's a spring there, and they give you a distance, like of the spring, and then you add a mass to it from A to B, and then it goes down to a lower point. Okay. Now, the second point is the equilibrium point, because you can see that it's balanced out. Okay. That mg is balanced out there, the force of gravity. Okay. And it goes down. So the amplitude is going to be the difference in height from the bottom of the block to the bottom of the block. Actually, I think that picture is wrong. I was actually going to mark on it, and I'm going to. Okay. It would actually be this distance here. Okay. It'd be from the top of the block to the top of the block. That would be the amplitude. Okay. Now, if you have the whole range of motion, like from the top to the bottom, the amplitude is usually half of that range. So if it's 10 centimeters to get from the bottom to the top, the amplitude is usually 5 centimeters. If it's 10 centimeters to get from the left edge to the right edge, the amplitude will be 5 centimeters. Now, how do you know the time is the period of motion? Again, the period is the time to get from one end to the other and back. So it's the time, if it's a pendulum, to go start on the left edge, swing over to the right edge, and then swing back over to the left edge. That's how you know it's a full period. Okay. If it's a time to get from one side to the other or one end to the other, the period's going to be twice that time. If it's a time for two complete motions, get from one side to the other and back, and then one side to the other and back, then the period will be half that time, and so on. So that's how you use any time to come up with what the period was, as long as it describes the actual motion of the object. And how's period related to frequency? Well, you can see from their definitions that they're kind of related. The frequency is the amount of time, is the amount of number of motions in a given time, and the period is the amount of time in a given motion. So they're inverses, which turns out pretty nice. Period is going to be 1 over the frequency, or the frequency is going to be 1 divided by the period. Again, they just work out the same way each time. So if I have a period of 5 seconds, frequency is going to be 1 divided by 5 seconds, or 1/5, 0.2 hertz. It kind of makes sense. If the period's 5 seconds, you're going to go through 0.2, 1/5 of a cycle during that 1 second. That should be how it works. And I don't think I put a slash there, but I'm going to need a slash there. So it was 1 over period. Okay. So next, let's look at an example of how to use like a text to look at to find out those qualities, the amplitude and the frequency and the period of something in simple harmonic motion. There's a little picture on the right-hand side of a mobile on a crib. It sways back and forth, moves 8 centimeters from side to side, and it takes 3 seconds to get from the left side to the right side and back. Okay. So first, let's look at the amplitude of it. Well, it says the 8 centimeters is what it moves from side to side, and that's the total distance that it moves. So the amplitude would have to be half of that, because the middle would be the equilibrium point. So it's going to move 8 centimeters divided by 2, and that's going to be 4 centimeters. That's going to be the distance from the equilibrium point, the center, to the edge, because it moves 8 centimeters the whole way. Next, let's look at the period. Okay. Now, they say that it takes 3 seconds to get from the left side to the right side and back. So it goes from the left to the right and then back to the left. So that's the total cycle that it moves. Like, that's the whole period. So 3 seconds is going to be the period. And then we need to find the frequency. That's the last thing. And find frequency, I'm going to take 1 and divide it by the period. So I'm going to take 1 divided by 3 seconds. 1 divided by 3 is 1/3, or 0.33. And my units are going to be hertz, or cycles per second. Those are the units I have to find that. So I found amplitude, period, and frequency based on the text that was written above. Let's do another example of that. You can see the little picture that's shown on the side. There's a small mass that's hanging from an elastic band, a little rubber band over there. It's stretched 2.5 centimeters from its hanging point and then released. And then takes 5 points to get from the top to the bottom of its motion. So they phrase it a little bit differently than last time. So let's think about what that means in terms of these concepts that we have to learn. First, let's look at the amplitude. This time they tell us that it moves 2.5 centimeters from its hanging point. Well, its hanging point is going to be its equilibrium point. That's the point that's going to try to get back to every time. So its amplitude in this case is going to be the exact distance they gave us, the 2.5 centimeters. This time they give us a time, the period. The time they give us is 0.5 seconds, but it's to get from the top of its motion to the bottom of its motion. Now last time they told us it was right from the left to the right and back, but this time they tell us from the top to the bottom, but not back to the top. So that's not the whole cycle, that's only half of it. So 0.5 is half, then I have to double it. So twice 0.5 is going to give me 1 second for the total motion of it. Then to find frequency, I'm going to use the same formula I used before. 1 divided by period. So I take 1 divided by 1 second, and 1 divided by 1, that's not hard math, that's just 1, and the units are hertz, or 1 cycle per second. So look at some examples, see if you can find out which ones are simple harmonic motion or not, and see based on the description whether you can find out whether there is the amplitude, the period, and the frequency of different objects that are moving in simple harmonic motion.